We're standing here at the entrance of the tunnel that leads to the Super Kamiokande detector. It's about 2,000 meters down this tunnel and to the left.
The world's leading physics lab, CERN, has activated what many believe to be a mind-blowing neutrino quantum field. This groundbreaking event might just redefine our understanding of existence, shattering everything we know about particles and forces. Could we be standing on the threshold of a revolutionary breakthrough? The ghost particle. Neutrinos are often called ghost particles because they pass through matter almost entirely unnoticed. They have extremely small mass, no electric charge, and interact so weakly with other particles that trillions of them flow through everything around us each second without leaving a mark. Unlike electrons or protons, which have clear, measurable effects on their surroundings, neutrinos are elusive, slipping past atoms at nearly the speed of light. Their weak interaction makes them uniquely challenging to study, but also highly interesting to physicists around the world. Scientists classify neutrinos into three types, which are called electron neutrinos, muon neutrinos, and tau neutrino. Each type is linked to a corresponding charged particle, the electron, muon, and tau. One of the most fascinating things about neutrinos is that they can switch between these three flavors as they travel, a process known as oscillation. This means an electron neutrino created in the core of the Sun might transform into a muon neutrino or tau neutrino by the time it reaches a detector on Earth. Neutrinos come from several natural sources. The largest flux comes from the Sun because the nuclear fusion reactions at its core produce enormous numbers of these particles every second. Neutrinos are also formed during beta decay inside nuclear reactors here on Earth, and they appear in cosmic ray interactions in our atmosphere. When very massive stars explode in spectacular events known as supernovae, they release vast numbers of neutrinos that spread outward into space. These supernova neutrinos provide astrophysicists with clues about the inner workings of exploding stars and the formation of neutron stars or black holes. The ghost-like nature of neutrinos is tied to one of the four fundamental forces of nature, the weak nuclear force. This force allows neutrinos to pass through dense materials without much disruption. Because of these properties, neutrinos offer a direct look into processes that are hidden from the reach of other particles. For example, when neutrinos are produced in the Sun's core, they escape freely, carrying information about nuclear fusion that photons can only provide after millions of years of bouncing around inside the Sun's interior. By the time solar photons leave the surface of the Sun, the information about the fascinating core processes is significantly blurred. Neutrinos, by contrast, escape almost immediately. This unique ability to probe otherwise inaccessible places explains why neutrino research is so pivotal. By studying these tiny particles, scientists hope to uncover secrets about the birth of the universe, the nature of matter, and even how particles gain mass. Neutrinos have already surprised researchers with their tiny but non-zero mass, and they continue to hint at physics beyond the standard model. Their near invisibility opens a route to observe phenomena that other particles would never reveal. Despite the challenges, scientists are determined to capture and understand neutrinos because their story is also the story of how the universe works at its most fundamental level. The history of neutrino research. Neutrinos were first proposed in 1930 by physicist Wolfgang Pauli. At the time, there was a mystery in beta decay experiments where energy and momentum appeared to vanish. Pauli's daring prediction was that a tiny neutral particle carried away the missing energy, preserving the laws of conservation. This idea was radical because no one had observed such a particle. A few years later, Enrico Fermi developed a theory of beta decay that included what he called a little neutral one, later named the neutrino. For many years, Neutrinos remained a theoretical concept. Their predicted weak interaction meant they were nearly impossible to detect with the technology of the early 20th century. However, in 1956, Frederick Rains and Clyde Cowan finally confirmed the existence of neutrinos in a landmark experiment. They set up detectors near a nuclear reactor, knowing that the reactor would emit large numbers of neutrinos, specifically electron antineutrinos, during fission processes. By observing characteristic flashes of light from neutrino interactions, Rains and Cowan provided the first direct evidence that Pauli's particle was real. This achievement was so significant that Frederick Rains later received the Nobel Prize in Physics for this discovery. The following decades brought more breakthroughs. Initially, scientists believed there was only one flavor of neutrino, but in the 1960s, they realized there must be more. First came the muon neutrino, linked with the muon particle, discovered through accelerator experiments. Later, the tau neutrino was confirmed, completing the trio of known neutrino flavors. Each discovery refined the understanding of how neutrinos fit into the family of fundamental particles. An important milestone was the study of solar neutrinos, most famously through experiments like the Homestake Mine experiment run by Raymond Davis Jr. in the 1960s. Davis set up a tank of perchloroethylene deep underground to capture solar neutrinos. The experiment found fewer neutrinos than theoretical models predicted. This so-called solar neutrino problem sparked decades of research and sparked theories that neutrinos might be changing flavors en route from the sun's core to Earth. This research culminated in the confirmation of neutrino oscillations at detectors like Super Kamiokande in Japan, which observed neutrinos generated by cosmic rays in the upper atmosphere. The real clincher came with the Sudbury Neutrino Observatory in Canada, which measured all three flavors of solar neutrinos, demonstrating that the electron neutrinos produced in the sun were partially transforming into other flavors by the time they reached the detector. These discoveries proved that neutrinos not only exist, but also have mass, although extremely small. Over time, neutrino research grew into a global enterprise. Collaborations formed to study different sources of neutrinos, from nuclear reactors and accelerators to the atmospheres of distant galaxies. By the late 20th century, neutrino physics had become one of the most dynamic subfields, offering evidence that the standard model is incomplete. Accelerators, underground detectors, and massive water tanks around the world have continued unveiling more details about these ghostly particles. As interests shifted to neutrinos' tiny masses, researchers also considered the implications for cosmology and astrophysics. The story of the neutrino is not just one of a single observation, but a long journey of theoretical predictions, experimental challenges, and scientific ingenuity, each step built upon the last, leading to where neutrino research stands today, poised to unlock even greater surprises and refine our view of how matter and energy behave at the most basic level. CERN's activation of a neutrino quantum field. A significant development in neutrino research has been the claim that CERN managed to activate and isolate the neutrino quantum field under controlled conditions. This experiment has been described as a major leap in understanding how neutrino fields behave when subjected to specific types of energy input. While standard neutrino experiments typically detect streams of neutrinos passing through a detector, this new approach aims to stimulate the neutrino field itself to examine phenomena that might remain hidden in typical observational settings. Scientists at CERN employed a specialized particle beam designed to deliver precise energy levels into a target area where neutrino production and detection equipment were placed. By using high-intensity beams of protons colliding with a specialized target, they generated neutrinos in a controlled environment. Unlike previous experiments that merely observed neutrinos in flight, this initiative specifically looked for ways to activate the underlying neutrino field, meaning They wanted to measure quantum fluctuations directly tied to neutrino interactions. Technically, researchers have tried to create a region with very low background noise and extremely stable electromagnetic conditions. The purpose was to isolate the weak interactions more clearly, allowing for potential observation of neutrino field disturbances that could be masked under normal circumstances. Specialized detectors, possibly an upgraded extension of existing technologies like those in the Opera or Isolde experiments, were placed around the target region to pick up even the faintest signal. Sensors measured outgoing particles, the presence of different neutrino flavors, and any anomalies that might hint at new phenomena. Early reports suggested that the experiment yielded some intriguing data. There were mentions of unusual patterns in neutrino production rates or flavor transitions under these specific field activation conditions. While peer-reviewed publication of these observations is still awaited, the initial impressions caused excitement among physicists. If neutrino field activation can be demonstrated, it could open a door to examining quantum field effects in real time, where scientists manipulate certain variables and watch how the field responds. The concept of directly stimulating a quantum field is not entirely new. Particle accelerators do something similar when they deliver enough energy to produce excitations that manifest as new particles. But the idea of specifically isolating the neutrino field and enhancing its signature in a controlled setting is quite innovative. It could potentially reveal hidden states or reveal coupling to undiscovered particles if any exist. It might also offer insight into why neutrino masses are so small relative to other fermions. Questions remain about how stable such an activated state is and whether it presents any safety or theoretical concerns. Critics warn that deliberate creation of high-density neutrino fields might pose risks if there are unknown, non-linear effects. Supporters of the experiment counter that the energies involved are still within the range of natural cosmic processes and that neutrinos are usually harmless due to their weak interaction cross-sections. The role of CERN in neutrino research. CERN, the European Organization for Nuclear Research, is famous for its work in particle physics, including hosting the Large Hadron Collider, LHC. Although the LHC primarily aims to collide protons at high energies, CERN has played a pivotal role in advancing neutrino science for decades. One noteworthy example is the Opera experiment, which took place in the Gran Sasso laboratory in Italy but involved neutrinos produced at CERN's facilities in Geneva. This experiment measured the time it took for neutrinos to travel from CERN to Gran Sasso, confirming that neutrinos obey the speed of light rules and are not faster than light particles, as one flawed early report once suggested. CERN has also supported various experiments that examine neutrino properties through its ISOLDE facility, where isotopes are studied in detail. Neutrino-related processes can be probed by looking at radioactive decays or other specialized reactions that produce neutrinos. Over the years, the organization has provided beams, detector components, and theoretical support to experiments around the world. Many leading neutrino collaborations rely on the expertise of scientists who either trained at CERN or use technologies developed there. Even though the LHC is not primarily a neutrino experiment, collisions in the accelerator can produce heavy mesons that decay into neutrinos, offering an additional source of data on neutrino production. Future upgrades to the LHC, along with possible new accelerator projects at CERN, might include dedicated beams for neutrino studies. This could allow for higher intensity neutrino fluxes or more refined detections that map out neutrino interactions in unprecedented detail. Beyond just facilities, CERN serves as a hub for collaboration. Scientists from many countries gather to plan unified experiments, share resources, and develop theoretical models. That global framework is one reason neutrino research has advanced so quickly, by bringing together expertise in detectors, data analysis, and theory, CERN fosters an environment where cutting-edge neutrino research can thrive. Additionally, CERN's experience with advanced computing, high-precision instrumentation, and engineering often rubs off on projects that operate outside of the Geneva site. For instance, neutrino experiments in Japan or the United States might incorporate designs influenced by CERN's technology. Data handling methods developed for the LHC can also be adapted to handle huge data sets from neutrino detectors that track millions of interactions over time. In recent years, some attention has turned to how neutrino research might benefit from new or proposed accelerators at CERN. There have been discussions about building higher-intensity proton accelerators that could generate neutrino beams with increased flux. These beams could then travel to underground labs in Europe to study flavor changes, matter-antimatter asymmetry, or other unsolved questions in neutrino physics. The synergy between these future projects and existing knowledge would allow for a deeper examination of neutrinos' role in the Standard Model and beyond. Neutrino oscillations and mass. Neutrino oscillation refers to the process in which a neutrino changes from one flavor to another as it travels. This phenomenon is rooted in the strange quantum mechanical mix of neutrino states. The flavors, electron, muon, and tau, are not exact matches to the neutrino's mass states. Instead, each flavor is a blend of distinct mass eigenstates. As neutrinos move through space, these mass eigenstates evolve slightly differently, causing interference patterns that make the neutrino appear first as one flavor, then another. Oscillations were first strongly indicated by the solar neutrino problem. Earlier experiments found fewer electron neutrinos from the Sun than expected. Physicists realized this shortfall likely meant some of the electron neutrinos were morphing into other flavors. Direct confirmation came in the late 1990s and early 2000s with experiments like Super Kamiokande studying atmospheric neutrinos and Sudbury Neutrino Observatory. SNO studying solar neutrinos. These results proved beyond doubt that neutrinos switch flavors en route, which in turn implied that neutrinos have mass. In quantum field theory, purely massless particles cannot oscillate in flavor. The discovery that neutrinos have mass was huge for particle physics. It proved that the Standard Model was incomplete in its original form. The Standard Model predicted neutrinos to be massless. Adding neutrino mass means adjusting the theory in ways that could hint at deeper structures, like the seesaw mechanism or other new physics beyond the Standard Model. The seesaw mechanism is a theory suggesting that neutrinos could be extremely light because there is a heavier counterpart that exists at a high mass scale, effectively pulling down the lighter neutrino masses. But the actual mechanism is still not fully pinned down, leaving open several possibilities. Measurements of oscillations tell us about the squared differences of neutrino masses, but not the absolute values. For example, we know the difference in squared masses between the first and second mass eigenstates and between the second and third, but we do not know exactly which one is heaviest or lightest. This leads to the concept of the normal hierarchy, where one mass is much smaller than the other two, versus the inverted hierarchy, where one mass is larger and the two others are close. Understanding the ordering of neutrino masses is a key goal for long baseline neutrino experiments like NOVA in the United States or T2K in Japan. There's also the question of whether neutrinos are Dirac particles or Majorana particles. A Dirac particle is distinct from its antiparticle, while a Majorana particle is its own antiparticle. If neutrinos are Majorana, processes like neutrinoless double beta decay could occur, where two neutrons in a nucleus decay into two protons and two electrons, but release no neutrinos because the neutrino annihilates itself. Detecting such decay would be proof that neutrinos are Majorana. So far, no conclusive evidence for neutrinoless double beta decay has been found, but detector sensitivities continue to improve. Oscillation experiments have reached an impressive level of precision. They provide values for the mixing angles that describe how much each flavor overlaps with each mass state, as well as a parameter called the CP violating phase, which could explain differences in how neutrinos versus antineutrinos oscillate. That difference might be related to why the universe is made mostly of matter rather than equal parts matter and antimatter. Challenges in detecting neutrinos. Detecting neutrinos is one of the most difficult tasks in experimental physics. By their nature, neutrinos scarcely interact with matter. You could send a beam of neutrinos through a wall of lead, many light years thick, and most of them would pass right through without a single collision. This extremely low interaction cross-section means detectors have to be huge, highly sensitive, and often placed in remote locations to shield them from backgrounds such as cosmic rays. Many detectors are built deep underground. For instance, Super Kamiokande in Japan sits over 1,000 meters below the surface, filled with 50,000 tons of ultra-pure water. When a neutrino occasionally strikes an electron or nucleus in that water, it can produce a faint cone of light known as Cherenkov radiation. Sensitive photomultiplier tubes line the walls of the detector's large cavity, picking up these rare flashes. The pattern of light reveals clues about the neutrino's direction, flavor, and energy level. In other experiments, like the underground laboratory at Gran Sasso in Italy or the Sudbury Neutrino Observatory in Canada, huge tanks of different materials record similar faint signals from neutrino interactions. Ice Cube in Antarctica does the same thing but uses natural Antarctic ice as the medium. Researchers drill holes into the ice, lower strings of optical sensors, and watch for flashes produced by neutrinos hitting ice molecule. Background noise is a huge issue. Cosmic rays continually bombard Earth, creating cascades of particles that can mimic signals. That's why going underground, or to the South Pole ice, helps reduce interference. Detectors are also equipped with electronics and software to distinguish a true neutrino event from other sources of light or radiation. Improving these methods is an ongoing effort, utilizing machine learning and more sophisticated electronics with faster response time. Another challenge is ensuring large enough event rates. Even with massive detectors, neutrino interactions are so rare that experiments may only record a handful of events per day, week, or month, depending on the neutrino source. For instance, solar neutrino experiments see only a few confirmed interactions each day in enormous volumes of material. Reactor experiments, which can place detectors close to nuclear reactors, might see more events because of the intense flux of antineutrinos from fission, yet it's still a painstaking procedure to differentiate signals from all the surrounding noise. Costs and engineering constraints also come into play. Constructing a neutrino detector large enough to catch numerous events is expensive and logistically demanding. Maintaining materials like ultra-pure water or specialized scintillating liquids is another layer of complexity. The high demands for cleanliness and stability mean that purely environmental factors, from temperature control to background radiation from rocks, must be tightly managed. Despite these difficulties, researchers have achieved remarkable successes. They have measured neutrino properties with high precision, caught one-of-a-kind events from supernovae, and even used neutrinos to probe the interior of Earth. Every advancement in detector technology opens up new questions about neutrinos' potential to reveal hidden parts of physics. This constant push for better sensitivity, larger detectors, and more refined data analysis keeps neutrino research on the leading edge of high-energy physics. Neutrinos and the early universe. Neutrinos were produced in huge quantities during the first few seconds after the Big Bang. When the universe was still extremely hot and dense, all kinds of particles roamed freely, including neutrinos, photons, electrons, and quarks. As the universe cooled, different interactions froze out at various stages, meaning particles like neutrinos stopped interacting often and began to travel through space. This created what scientists call the cosmic neutrino background, a faint sea of relic neutrinos that fill the entire universe. The cosmic neutrino background is somewhat like the cosmic microwave background, which is the leftover radiation from when the universe was about 380,000 years old. However, neutrinos decoupled from the rest of matter much earlier, roughly 1 second after the Big Bang, when their interactions became too rare to keep them in thermal equilibrium with the rest of the primordial plasma. Today, these relic neutrinos are thought to be incredibly abundant, but they have such low energy that detecting them directly remains a major challenge. They move very slowly compared to higher energy neutrinos. Because neutrinos barely interact with matter, they can carry information about the state of the universe when it was just a fraction of a second old. If scientists could detect these relic neutrinos, it would be like having a snapshot of the universe at an incredibly early stage that could confirm or refute theories about how matter, antimatter, and radiation behaved at some of the highest energy scales we can imagine. Neutrinos also influence structure formation. In the earliest epochs, neutrinos moved close to the speed of light, acting as hot dark matter. Their sheer velocity smoothed out some of the clumps that might otherwise have formed in the primordial plasma. As the universe cooled, neutrinos gradually lost energy and became non-relativistic, meaning they slowed down. The interplay between neutrinos and other forms of matter, like dark matter that doesn't interact much with anything except through gravity, influenced the formation of galaxies and large-scale structures. Measuring neutrino properties helps refine models of the early universe. For instance, the sum of neutrino masses can affect the rate of structure formation. If the neutrino masses are higher, they would have a different imprint on the distribution of galaxies or on the cosmic microwave background. Cosmological data, such as that from the Planck satellite, can place upper limits on the combined mass of neutrinos. Comparing these cosmological constraints with data from neutrino oscillation experiments is a way to cross-check our theories. Practical applications of neutrino research. While neutrinos are primarily studied for their fundamental interest in physics, there are also some practical applications and future possibilities that excite scientists. One example is the use of neutrinos for nuclear reactor monitoring. Since nuclear reactors emit a steady flux of neutrinos during fission, these particles can penetrate thick shielding and provide real-time information on the reactor's operations. Any change in reactor fuel composition affects the energy spectrum and rate of emitted neutrinos, which could allow for a new level of transparency in nuclear safeguards. Another application involves probing the Earth's interior. Geoneutrinos, produced by the radioactive decay of elements like uranium and thorium in the Earth's crust and mantle, can help map out the geological processes happening deep below the surface. Detectors in underground labs can pick up these signals, giving insights into how much heat the Earth generates from radioactive decay and how that heat drives plate tectonics and volcanic activity. Though still a young field, geoneutrino research has the potential to refine models of geophysics and Earth science. There is also ongoing speculation about using neutrinos for communication. Because they pass through matter so easily, neutrino beams could, in theory, send messages through the Earth's crust without the need for cables or satellites. A few feasibility experiments have shown that neutrino-based communication is possible, but it is extremely challenging given the technology needed to generate and detect neutrinos. Still, in very special circumstances, such as reaching deep submarines or building secure communication channels, neutrino technology might someday become useful if detection becomes more practical. In medical imaging, neutrinos currently do not offer a straightforward application because their weak interactions mean you would need a massive detector to see them, and the energies typically studied in neutrino experiments are not ideal for imaging human tissue. However, research spin-offs from neutrino detection, like photomultiplier tubes and sensitive electronics, can benefit other areas of physics and medicine. Technology developed to reduce background noise in neutrino experiments has found uses in radiation detection and security systems. Some have proposed that in the far future, if neutrino beams can be made more intense and detectors more compact, we could harness neutrinos for tasks like remote scanning of asteroid interiors or even large-scale geological surveys. Such futuristic ideas may or may not materialize, but they show the creativity that emerges from neutrino research. When you develop techniques to detect nearly undetectable particles, you often end up pushing technology in ways that spill over into other domains. Practical benefits also extend to training skilled scientists and engineers. Building huge underground neutrino detectors fosters innovation in fields like cryogenics, electronics, data handling, and materials science. The expertise gained can then enhance many areas of technology and industry. Large collaborations in neutrino physics also serve as a model for global cooperation, which can translate into other big scientific ventures. While neutrinos remain mostly in the realm of pure research, these examples show that basic science often leads to unexpected applications. In the long run, knowledge about neutrinos' behavior and the technologies created to detect them could have more direct benefits for society than we currently imagine. Neutrino research's potential for cross-disciplinary influence means the field offers more than just cosmic insights. It can also drive new ideas that help solve practical problems. In the end, neutrino physics is expanding on many fronts. Every new experiment, whether it's discovering a subtle effect in neutrino oscillations or ruling out a potential sterile neutrino signature, adds to a bigger picture of how these ghostly particles fit into the cosmic puzzle. The next decade or two could bring about breakthroughs that reshape our sense of fundamental physics, bridging gaps between particle physics, astrophysics, and cosmology. Neutrinos, due to their persistent mysteries, remain central to that quest, poised to lead us into a deeper understanding of how the universe operates at its most basic level. Thanks for watching another episode. While you are still here, make sure to click the video on your screen for more quality content.